It's a really great pleasure to see so many wonderful old friends and so many wonderful people and so many wonderful speakers. That's really, really a massive pleasure to see everybody. We've got 6 speakers today. Each speaker is going to take about 20 minutes to speak, and we've allowed 10 minutes after each talk for questions. There are lots and lots of people who are going to be here, and I'm sure there'll be lots of questions. So if you could use the mechanism of raising your hand if you want to ask a question, Elaine and I will do our best to make sure we get to everybody. I have a feeling that may be an imperfect process, but I promise you we'll do our best with so many people. We have a break about 2/3 of the way through, at just after 3 p.m., 1500 London time. So that's after the first, oh, sorry, I haven't 2, of course, as well. So we have 1, 2, 3 talks and then a break, and then another 3 talks and then a break, and then 1 more talk and a discussion session, which will take us up to 1600 London time. So I think we are almost ready to start. Our first speaker being Piecha. Piecha, are you ready to share your slides?
Yes, of course. Yes,
great.
So
if the other speakers could be ready to share the slides, that would be great. Let me or Elaine know if there is any problem, and we'll do our best to help. Other than that, I think we should very shortly hand over to Piecha. Elaine, do you want to introduce Piecha?
So I start. Oh yeah. Okay. Perfect. Yeah. So
yeah, sure. So
pardon?
No, I was just going to introduce you.
Oh, so sorry. So I didn't want to interrupt you. So sorry. Yeah.
No, it's okay. I just first of all say thank you to everyone that is here, and to say that it's a very great pleasure to introduce the first speaker, that is going to be Professor Peter Schroeder-Heister from the University of Tübingen. And so, Professor, if you want to start, please go ahead.
Yeah. Okay. Yeah. Thank you very much. So welcome to everybody wherever you are. This World Logic Day is a great success story. It was an excellent idea by Jean-Yves Bézieux to put this on track a couple of years ago, and this has even been boosted by the corona pandemics. Now we have great logics on all channels simultaneously. So I say something about proof-theoretic semantics, which is essentially the meaning of this colloquium. It has a slightly different title, but this is what it is. If you look at proof-theoretic semantics, then you realize today, at least, that it is a well-established discipline together with a well-established name. There is already a textbook on proof-theoretic semantics by Nissim Francis. There are plenty of articles. So nobody seems to complain anymore about this name, but this has not always been like this. I suggested the term, or at least I think so, that I suggested it in the middle of the 1980s. At that time, people were not talking about proof-theoretic semantics, though the term was, though the subject was definitely already there. For example, if you look at, and even certain terms, so the relationship to semantics was already there. So if you look, for example, at an article by the German logician von Kutscher in 1968, he then proposed the term Gensen semantics, which is essentially what proof-theoretic semantics nowadays is, referring to work by Curry and Lorenzen. And if you look at Curry's preface to his Foundations of Mathematical Logic of 1963, there Curry says that Gensen rules are a tool of the semantic analysis, and this is essentially the program of proof-theoretic semantics. There's also the earlier work of Karl Popper of the late 1940s, which is closely related to what we nowadays call proof-theoretic semantics. There will be a talk later today by Thomas Piecha on this issue. So why should one call the issue proof-theoretic semantics? If one looks at the term semantics, this is the name of a philosophical discipline which was introduced by Tarski and Carnap in this order. So Tarski in 1936 at the World Congress of Philosophy then spoke of the task of establishing a scientific semantics. And Carnap later on in his 1942 book, Introduction to Semantics, described the purpose of this book as to furnish a theory of this kind called semantics. And this kind, by this kind, he meant the signifying, the analysis of the signifying function of language. And he also said it has to do with a theory of logical deduction. So something which is very important actually nowadays for proof-theoretic semantics. So semantics was established by Tarski and Carnap. And then the question for me in the 1980s was, I mean, why on earth did all the advocates of proof-theoretic semantics then not call their enterprise semantics? And this is a sort of criticism that applies in particular to Dummett, who created a special term for this. He always spoke of theory of meaning, and all his readership followed him in that respect. But I think that was the wrong attitude, not pretending that one is creating a completely new foundational discipline, but one should have said, well, there is this well-established and perfectly fine term semantics, and perhaps Tarski and Carnap did it in the wrong way, in the denotational way, so let's do semantics in the proper constructivist or proof-theoretic way. So my attitude then was, don't leave the term semantics denotationalists alone. And that's why I proposed one should speak of proof-theoretic semantics. And I'm quite happy that the term has caught in the meantime, actually. So why proof-theoretic semantics? Why this subject at all? I would say simply because it has its proper place in the taxonomy of the philosophical study of meaning. So it somehow belongs to a certain branch of philosophical and logical development. So if you look at the meaning as use approach, or at the idea that meaning is somehow related to using terms in language, then we have this big movement that came from Wittgenstein, but had already been there, of course, throughout the whole history of philosophy in a certain sense. So since Wittgenstein, at least, we have this meaning as use approach. Then we have this special form called inferentialism by Brandom, which is still a very general thing. So Brandom somehow classifies the whole philosophical tradition into inferentialism and non-inferentialism. And then we have the logical branch of inferentialism, which is then proof-theoretic semantics, or perhaps not just a logical branch, perhaps a certain fraction of the logical branch. So in a sense, it belongs to what one should discuss in theoretical philosophy. So there is no need to justify this enterprise of proof-theoretic semantics. Proof-theoretic semantics has two sides. You can understand it as semantics of proofs, and you can understand it as semantics in terms of proofs. As semantics of proofs, it is closely related and perhaps not the same, but a division of what Dag Prawitz has called general proof theory in distinction to a reductive proof theory. General proof theory is the study of proofs as entities in their own right, in contradistinction to proofs as something that have a certain deductive power, or proof system that have a certain deductive power are consistent or inconsistent or whatever or so. Of course, these two aspects, semantics of proofs and semantics in terms of proofs, are overlapping. So you can do semantics of proofs in terms of proofs, and you can, but you can also do a semantics of just propositions in terms of proofs. So there are different issues in these two branches of proof-theoretic semantics. So let's look at proof-theoretic semantics as the semantics of proofs, I would say there are plenty of problems, of course, but I would like to, I think one can identify at least 3 crucial problems that belong to the semantics of proofs and thus to proof-theoretic semantics in this sense. The first one is, of course, the format of proofs. So we must look how syntactically, what proofs look like syntactically. So the format of proofs, for example, natural reduction, is this the primary system that we need to consider in proof-theoretic semantics, or is perhaps the sequent calculus more primary and perhaps other systems secondary? What about reductive approaches such as tableau approaches or game theoretical approaches, and so on and so forth? And actually the semantics closely hinges on that. For example, if you, there's a big movement in proof-theoretic semantics that's categorical proof theory. And this is perhaps a certain sort of movement that takes the sequent calculus more primitive than natural reduction. Categorical proof theory is, if I see it correctly, also represented in our colloquium as the last talk by Edmund Robinson. The second problem that I would like to identify is the problem of the identity of proofs. Quine has said there is no entity without identity. And if we don't want to identify proofs with their syntactical form, then we must say when 2 syntactically different proofs represent the same argument are identical. So proof theory, proof identity should be a big issue of proof-theoretic semantics. There is also a talk at this colloquium on this by Sara Ayhan, actually. And the third big question is the validity of proofs, which is the topic of Dag Prawitz's talk. Once we know what a proof looks like and what the when proofs are identical, we need, of course, know when proofs are valid, because I mean, if we want to use a proof to show that a certain proposition is true, then this proof must be a valid proof and not just something else. So this is the third big topic, and there are very many more big topics, but I mean, these are those I would say lie at the core of proof-theoretic semantics as the semantics of proofs. So if we look at proof-theoretic semantics as the semantics in terms of proofs, then actually some other aspects come in. So the main aspect is the aspect of the atomic base, something that Tor Sandqvist is going to talk about later on. In proof-theoretic semantics, the atomic base plays a novel role. In traditional model-theoretic semantics, the atomic base is the structure or the model in which formulae are evaluated. Whereas in proof-theoretic semantics, in the sense, this is the same. They are evaluated with respect to the atomic base, but the atomic base has a much greater expressiveness, as the atomic base is itself a proof system and not just a collection of true or false atomic formulas. So we get a new level of sophistication by considering proof-theoretic atomic bases, which make the whole enterprise different from standard model-theoretic semantics. And what we then immediately get access to is the issue of inductive definitions, which is very important both in philosophy and mathematics. Inductive definitions are nothing but elementary proof systems that one should be able to incorporate in the atomic base so that one can evaluate formulas with respect to inductive definitions. Fundamental problems that then arise are in particular the problem of semantical completeness. So if we have a certain sort of proof-theoretic semantics, what is the formal system of logic that this semantics justifies. Is it intuitionistic logic? Is it classical logic, or whatever or so? And this is a problem which is not fully solved. It's not trivial. It's not a trivial matter that we reach intuitionistic logic. It's not trivial that we perhaps reach some stronger logic or so. There's a lot of issues that need to be settled, and also of course the problem of interpreting classical logic. So one idea is to interpret classical logic within a system which can also accommodate other systems of logic. Luiz Pereira is going to talk later on what he calls ecumenism. So the idea is that you have several churches which are ideological systems, so perhaps classical logic as the Catholic Church, and then you have these Protestant churches like intuitionistic logic, and you are asking for the system in which they can perhaps coexist in peace. So this is one problem. There are many other problems that I cannot mention here. What I would like to mention is one problem that I think has to do with practically all aspects of proof-theoretic semantics, and that needs to be further addressed, which is the problem of proof reductions. So everybody who has done a natural deduction knows what a proof reduction is. So suppose you have introduced a conjunction from proofs of A and B, and then eliminate the conjunction again. Then you can just remove the whole thing, extract the proof of A that you had before, and take this as replacing what you had originally. So the idea is that this proof can be transformed into this proof by means of reduction, where this reduction in this case is a kind of extraction of a proof from the original proof. But in general, the question is, what is a reduction? So what is allowed as a reduction? Can we do any sort of transformation? Is it extraction? Is it perhaps composition of proofs or whatever? This is not absolutely settled. So there is no undisputed answer yet. We probably don't want anything, or perhaps we want it, I don't know. I think we should not want anything like this here. So suppose you have a proof of A, and then you proceed with your proof, and then after a number of steps, you arrive at the very same A later on. Then you say, well, this we can just extract this first proof of A, and say this whole proof reduces to this first part of the proof. So just say this and this proof are identical by means of a certain proof transformation. You can do this, but when you do this, you run into all sorts of difficulties that I cannot discuss here, at least as long as we do not know what is happening in between this A and this A here. But I mean, if we don't want to have something like this, the question is, what do we want exactly? So what is a proof reduction exactly? And the standard answer is that somehow reductions or proof transformations are tied to definitions. One says they are tied to the sequence of steps that leaves from a definiens to a definiendum and back to a definiens. So this is the thing that you have in the case of conjunction. You introduce something, so you pass from the definiens of conjunction to the conjunction, and then back to the definiens. And this is somehow what you would like to have when reduction or transformation of proofs is allowed. But even then, you see all sorts of difficulty. You arrive at not necessarily difficulties, but problems that need to be discussed. And this is what, following Lord Holland, as I call definitional reasoning, considering definitions. And look what can happen. So define in propositional logic a propositional constant A by some perhaps more complex formula B. If this is a definition, then you might say that you have a sequence that moves from definiens to a definiendum back to the definiens from B using one direction of the implication of the implicational definition to the definiendum and back to the definiens. And then you could argue, well, this whole thing, because you have this step definiens, definiendum, definiens, reduces to what you originally had. So you can somehow eliminate this piece of proof in terms of by this piece of proof. This is nice in a certain way, but Jan Ekman had shown that at least in certain cases that leads to surprising consequences. So if you take a limiting case of a definition, namely define A by its own negation, which is in a sense a sort of translation of semantical and other antinomies, then you have the following thing. Suppose you use A if and only if not A just as an ordinary assumption, then you have a trivial derivation of absurdity from this A if and only if not A. This is absolutely trivial, but as soon as you consider this assumption here to be a definition, so you consider A defined by not A, then you obtain a derivation which is not normalizable, which is due to the fact that as soon as you use certain definitional informations here, so if you have certain definitions, then you can then you have this additional reductions that come together with the definition, because we have said reductions have to do with definitions. You have additional reductions, and these reductions somehow destroy the normalizability feature that you have in intuitionistic propositional logic. This is perhaps not necessarily unwanted, as it reflects somehow certain properties of definitions, but in any way, it's these sort of phenomena in the context of definitional reasoning should be considered more closely. These are all intentional aspects, as one should say, of proof-theoretic semantics, as they have to do with the behavior of deductive systems and the identity of proofs in the presence of certain definitions of meaning assignments. So I think this is one of the main topics that, to my mind, should be pursued at least in the philosophical branch of proof-theoretic semantics in the future. All these problems, as I said, hinge on what we want to accept as a proper reduction or transformation of proofs. So one of the big problems is what is a reduction or what is a proof transformation? And I stop with this. Thank you very much.
Thank you very, very much, Peter. I think, David, we have 2 minutes to go. Can I just post a question that was in the chat?
Yeah.
And,
yep.
I think it's a great idea, right? So, so Peter, there is a question in the chat by Andrei, and he asked you, how do you place the justification logic, as in the book for Artemov and Fitting, with respect to PTS? Is a proof in the sense of PTS a special case of justification?
Yes, I have somehow, I don't know, it's easy. Yes, this all belongs to the big to the big area of proof-theoretic semantics. So my impression is, I mean, this has grown into such a big subject that this all definitely fits into this. Talking about justification logic goes too far for this occasion or so, but I mean, one has to start about it starts with the labeling of deductive systems, but then of course, I mean, you have the logic of justifiability, and you have justification logic, and this definitely fit into the picture somehow, but I don't think I can say more on that now. Yeah.
Thank you.
So Joran has his hand raised.
Just a comment on Michael Dummett's use of the phrase theory of meaning in place of semantics. Dummett didn't invent the phrase theory of meaning. It was quite well established in Oxford at the time. And I think it might go back to Gilbert Ryle's quite hostile review from 1947 or 49 of Carnap's Meaning and Necessity. And then Ryle also wrote a survey article in the mid-50s called Theory of Meaning. So that's, it was a standard Oxford term, so to speak.
Okay, so it was an Oxford term, yeah. Okay,
and brought to Oxford by Donald Davidson.
Yeah, yeah.
Great. So thank you, Peter, and thank you all for the nice comments and questions. So we're going to move on now. So next speaker is Dag Prawitz. So Dag, thank you so much for accepting the invitation. Welcome. And if you want to share, you're going to talk or you're going to share a screen or you have slides? You're muted. You're muted, Dag.
So do you hear me? Yes, do you hear me?
Yes.
Yes, good. So I have a PowerPoint presentation that I want to share with you and see if I can get it clear. Yes. So it's yes. Yes. So I will speak on the validity of inference, more precisely on the problem of explicating the concept of valid inference. I intend this to be very elementary, so that on this logic world day, it should be possible to follow by anyone who is curious about proofs or logic in general, but is not doesn't know much about it. So that's my intention. We'll see what will happen. So see what I can. Yeah. So. So by an explication, so I am back here, I think. So by an explication, I mean the same as Karna, who introduced the term. So to explicate an imprecise, intuitively used concept is to find a new precise concept that is fruitful within some kind of scientific or philosophical theorizing, and is at the same time in agreement with a former intuitive concept in essential respects. So as you already saw here, I see the well-known definition of logical consequence due to Bolzano and Tarski as a good example of a successful explication of the intuitive notion of something following logically from something else. So we have here a precise definition that most of you perhaps know. A sentence A is a logical consequence of a set of gamma of sentences. If and only if A is true under any interpretation of the non-logical terms of A and the sentences of gamma, under which all the sentences of gamma are true. So it depends essentially only on the notion of truth under interpretation, or truth in a model, as one also says, which is accounted for in model theory, and gives rise to a very fruitful concept within that theory. Furthermore, what comes out as logical consequences agrees to a greater extent with the cases where a sentence is deemed intuitively to follow logically from a set of sentences. There is no comparable explication of the intuitive concept of valid inference, in spite of the fact that it is the most fundamental logical concept upon which our idea of proof is built. For a deductive argument, so deductive arguments, as we have understood them since the time of ancient Greece, are chains of inferences. In other words, collection of inferences connected to each other by the conclusion of one inference being the premise of another one. And proofs are deductive arguments whose inferences are all valid. So for a deductive argument to be valid or to amount to a proof, its inferences must, of course, be valid. So without the concept of valid inference, we cannot speak very well of proofs or the meaning of proofs, which is the title of this seminar. And unfortunately, I cannot present here any explication of the concept of valid inference. I wish I could, but I can't. That I say something short about the concept of inference and about the direction in which I think one may be able to explicate the concept of valid inference. So to start with the concept of inference. So to make an inference, that is a conclusion from a number of premises, can be seen as a mental or as a mental act or as a speech act. I will look upon it as a speech act, but the choice doesn't matter here when we are concerned with valid inferences. A deductive inference, understood as a speech act, consists of a number of assertions, one of which, the conclusion, is presented as conclusively supported by the other ones, the premises. The assertions do not need to be categorical. Deductive arguments often start from assumptions, and the assertions of the inferences will then sometimes be assertions under assumptions. I shall not have time to go into that very much, although it is a very essential point. So certain things will be somewhat oversimplified in that respect. That the conclusion is understood to be supported by the premises is often indicated verbally by inserting small words like therefore, hence, or since, for instance. So typical forms of inferences indicating the support have this form. To say A1, A2, and so on, AN, hence B, or B since A1, A2, AN. These are forms of inferences where A and B are assertions. And as is accentuated here by these small words, hence, and so on, when making an inference, the conclusion is claimed to somehow be justified. What is asserted by the conclusion holds because what is asserted by the premises hold. Not only do we claim that the conclusion is supported by the premises and thereby justified, to provide for the justification of the assertion appearing as conclusion is also the aim of an inference. I say here, provide for the justification instead of just justify, because the idea is that the conclusion is to become justified given that the premises have already been justified. The inference alone does not justify the conclusion. If there is an inference of a deductive argument whose aim is not achieved, we speak of a gap in the argument. And if a gap cannot be filled in somehow, the argument has to be withdrawn. That happens sometimes. So the first explanation that comes of the validity, it could be in this way. So a short natural answer to the question, what is it for an inference to be valid, is to say simply, an inference is valid if and only if it achieves its aim. In other words, if and only if the premises do support the conclusion and thereby provide for its justification. We can spell out this a little more precisely by saying that for an inference to be valid, the justification of the conclusion must be directly available, given justification to the premises. No further inferences that we needed to justify the conclusion. That the justification of an assertion is available means, metaphorically speaking, that it can be seen that the assertion holds. So for an inference to be valid, it must be possible to see directly, without any further inferences, that the assertion holds, given that we already have seen that the assertions made by the premises hold. To say this, to explain validity of inference in this way, is of course far from an explication of validity. But it's informative enough to see the great difference between an inference being valid and the relation of logical consequence being applicable to the corresponding sentences. That the sentence A is a logical consequence of Z gamma is not a sufficient condition for the validity of the inference from the assertion of the sentence of gamma to the assertion of A. So this is obvious, I hope. As we all know, it may be difficult to establish that the sentence A is a logical consequence of that gamma of sentences. A may be, for instance, be an advanced theorem in an axiomatic theory, and gamma may be the axioms. Then A is in fact a logical consequence of gamma. But to establish it, we need to make a deductive argument containing many steps, many valid inferences. So although the axioms are justified, and A is a logical consequence of gamma, of the axioms, there is no direct available justification of the assertions of the assertion of A from the justification of gamma. But nor is this a necessary condition that this logical consequence holds. For instance, mathematical induction is certainly a valid form of inference. We can validly infer that any arbitrary natural number has the property P if P holds for 0 and holds for n plus 1 when it holds for n. But this depends on the meaning of the expression natural number, which is a non-logical term, and may fail to hold if we vary the interpretation. It is worthwhile to note also that the relation of logical consequence is obviously transitive. If B is a logical consequence of A and C is a logical consequence of B, then of course C is a logical consequence of A. But the two inferences from the assertion of A to the assertion of B, and from the assertion of B to the assertion of C, may both be valid without the inference from the assertion of A to the assertion of C being valid. The justification of A may not be sufficient to get the justification of C. A valid deductive argument consisting of the first two inferences from A to B and from B to C justifies, of course, the assertion of C under the assumption A. So we have a justification of of that. We can say that it shows that the inference. So we can so a deductive argument consisting of the first two inferences justifies the search of C under the assumption A, and shows that the inferences from gamma to C, from the assertion of gamma to the assertion of C, is immediately valid, I would say. Immediately is a somewhat uncommon word, but it is fitting here as the opposite to immediately. The valid inference, as I have understood it here, justifies the immediate transition from the premises to the conclusion, because the premises justifies the conclusion. If the inference has to be broken down into simpler inferences in order that one needs to see that the transition is justified, we do not have an immediately valid inference, but only immediately valid one. The validity of inference and the relation of logical consequence are thus two very different concepts. I've spent some time on it because, strangely enough, many contemporary elementary textbooks of logic, and even many papers in philosophical logic, identify the two concepts. This is indeed strange, especially since already at the very beginning of logic, one seems to have kept them apart. Aristotle's often quoted definition of syllogism runs in the translation of Ross as follows. A syllogism is a form of speech in which certain things being laid down, something follows of necessity from them. Immediately after this definition, Aristotle continues by introducing what he calls a perfect syllogism. A perfect syllogism is one that needs nothing other than the premises to make the conclusion evident. I shall not enter into exegetical discussions about these definitions. I just want to point out that while Aristotle's definition of syllogism has been a forerunner, an inspiration to our notion of logical consequence, his notion of perfect syllogism has received much less attention and seems to introduce an epistemic notion to make evident in Ross' translation, which seems to make the drift of Aristotle's definition of perfect syllogism similar to that of my preliminary explanation of what it is for an inference to be valid. Although nothing like Aristotle's notion of perfect syllogism is present in the main trend of contemporary logic. Instead, the identification of valid inference with consequence is dominant, as I have said. There are contemporary critics of this identification. I want to mention here Peter Bökhosian, Martin Löv, and Göran Sundholm. Martin Löv, when he speaks on immediate inference, he says, you must make the conclusion evident to yourself without any intervening steps on the assumption that you know the premises. So he is using, like Aristotle, the notion of evidence. However, explanations of validity of inference, like the ones I have considered so far, in terms of evidence or justification, are far from expectations, as long as we do not have a firm theoretical grasp of the concept in terms of which validity is defined or explained, and can use them fruitfully. So here the words are evidence, or I have usually spoken of justification instead. And it is here that proof-theoretic semantics becomes relevant to the project of explicating the validity of inference, because of connecting the meaning of sentences with justifications of proofs of their assertions. The basic idea goes back to Gensen. And we can say here that to connect with Peter Schroeder-Heister's talk, that what is relevant here is both semantics as what he called semantics in terms of proofs and semantics of proofs. And my time is really up here, so I will not be able to say anything really about how proof-theoretic semantics is relevant, can be relevant for this project of explicating validity of inferences. But Peter Schroeder-Heister hinted to some of these things, because it is the thing that we explain the meaning of sentences in terms of what justifies them. So that's what Dammert called meaning theory as based on justification. So that's that is the thing that for an explication, as I have understood it, we need to really develop some basic term in which the validity is explained, and that will here be justification. What does justify an assertion, and connected with what does the assertion mean. So that's what I wanted to give an idea about. So thank you very much.
Thank you, Dag. It was really great. Thank you. I like it a lot. And the next talk is going to be given by Tor. Tor, do you have the slides?
I do. I will start sharing them now. There. Can you see that properly?
Yeah, we can. Thank you so much. So it's a pleasure to introduce you and welcome, and thank you so much for accepting the invitation, and the floor is all yours.
Oh, well, thank you so much for inviting me. Right, this is my title, Atomic Bases or Bases and the Validity of Peirce's Law. And what I'm going to be talking about is something that I have taken to calling base extension semantics. And this is not a new, not an original idea in any way, but I think it's a useful term to, in order to distinguish it from some other related ideas. And one way of describing what it's all about is that it's a Crippy semantics with certain assumptions about the structure of the states. Another way of describing it, which is perhaps more appropriate for the present company, is that it's what you get if you start out with an old idea of Dag Prawitz's on how to define the concept of a valid proof, and you strip away the proofs and end up with just the concept of or a notion of provability. I will be focusing for purposes of this talk on just one connective, the conditional, and I will also be we will also be dealing with the absurdity constant. So here is a description of what we mean in this context with a base. It's a set of rules of inference pertaining to particular atomic sentences. So we could, for instance, have a rule saying that from Tammy is a fox and Tammy is female, we may infer Tammy is a vixen. Or of course, we could have some mathematical sentences. Or we could have something like, there was just a flash of lightning. And from this, we infer there will shortly be a roll of thunder. So it doesn't, it's not part of the concept here that the inferences be analytically valid in any sense. They one will just conceive of them as being accepted and in some way supported. So given that we have a base like this, we can define we can define a relation between bases and sentences using this double turnstile symbol. I tend to read this as saying that B supports P. And well, if P is an atomic sentence, well, then B supports it just in case the sentence is provable in B using the rules of inference therein. And for conditionals, well, this is a familiar idea. The conditional is supported by a basis just in case it holds of every extension of that basis, or every basis that is a superset of it, that if it supports P, then it also supports Q. So it's no surprise that on this semantics, we get the minimal implicational calculus. We get closure under modus ponens and these two familiar axioms. That's a quite straightforward thing to prove. But we want a little bit more than that. To begin with, let's think about the constant, the absurdity constant, and more generally, negation. So the way we are going to introduce that into this context, one can do it in different ways. One can introduce it as zero-place connective and have a semantic clause for it. The other way is to say that, well, we're just going to focus on some specially designated atomic sentence in the language. And we decide that we are going to refer to it using the bot symbol, and then we call a base an EFQ base if it holds of every atomic sentence that the base contains the inference from bot to P. So ex falso quod libet, as long as the thing you wish for is an atom. So this is a subclass of bases, and now we're going to look at what holds of these EFQ bases, ex falso quod libet bases. Well, again, quite unsurprisingly, you get ex falso quod libet. Any conditional with this absurdity as its antecedent will be supported by such a basis. And so we have, in effect, intuitionistic logic for this fragment of the language containing absurdity and conditionals. So no surprises so far, but my title contains the reference to Peirce's law, which is not an intuitionistically valid law. It's what you need to add to intuitionistic logic to get classical logic for this fragment of the language. Well, that's one way of achieving it. So, and as it turns out, I'm not going to prove this here, but in fact, if in order that one of these EFQ bases should support Peirce's law in general, and therewith full classical sentential logic, it's sufficient that it should support Peirce's law for atomic sentences. So, if we get that for an EFQ basis, then we have classical logic. So then, what is the status of Peirce's law for atomic sentences according to this this semantics that we've just described? Is it generally valid? Well, it turns out that this is a somewhat complex question. We can't just say yes or no because we haven't actually yet specified what kinds of rules go into our bases. As it turns out, the validity of this atomic Peirce's law and with it Peirce's law in general depends on what sorts of atomic rules we decide to allow into our bases. So I've made a little table here. Suppose, to begin with, that we require that all of the rules in an atomic basis should be of this form. 0 or more premises, and from them you infer a conclusion. That's it. No cancellation of assumptions or anything like that. Well, as it turns out, if this is your idea of an atomic basis, then given this semantics that we've described, Peirce's law will in fact be valid. So this is a way of getting classical logic. Let's see, I've got consumed 19 of my minutes. I think this actually leaves us time to go through the proof, which is... No, okay, I won't.
Only 9, so you have more time. You have 11 minutes.
Sorry, yeah, thank you. That's what I meant. Yeah, so this proof is short and easy and constructively valid. Actually, let's save that until the end in case there is time. All I really need you to know is that it's short and easy and constructively valid. And will be uploading the slides?
Yeah, sure.
So people can consult this later on if I don't have time to go through the whole thing. So that's what happens if we require that the rules in one of these bases be of this simplest possible form. Now, here is a slightly more complex form of a rule. You will see that I have a mix here of Latin and Greek letters, and the way I want you to think of this is that A through B are some specific sentences, like the ones we had on our first slides. Tammy is a vixen, for example. Whereas phi is a schematic letter here. So the rule says that if you have these particular A, B, C, D, however many they might be, then for any atom phi, this rule is applicable. So we might, for instance, take Michael Dummett's example, with which many of you will probably be familiar, that A could be that there's a child playing in the lawn. And then we have no other, so A through B is just this one sentence. And then C could be that, well, there's a girl playing in the lawn, and D, that there is a boy playing in the lawn. So what this does in effect, is that it gives you the content of a multiple conclusion sequence. And it says that if all of these hold, then at least one of these must hold. So we can think of this as a generalization of the format in the first row. It's not quite that from a purely, what shall I say, bureaucratic point of view, but any rule of this form can be simulated with one of these. Now, if we decide that this is going to be, that we're going to allow this form of rules in our basis, then, as it turns out, Peirce's law will still be valid. I don't actually know whether this result has been properly published in print. It's part of my unreadable dissertation, but I haven't actually put this in a paper yet, but maybe someone else has pointed it out someplace. I'd be interested in knowing this. It's true in any case. Now, this is somewhat more general than the first format, but we can go more general still. We can say, well, you have any number of deductions here, And you can discharge any number of premises from any one of these deductions according to some specified pattern and infer G. Now, if we generalize our concept of a basis so as to allow for this kind of rule, then it turns out we no longer get classical logic. I have a paper showing that what we get is exactly intuitionistic logic, provided that the language is infinite and perhaps a few other conditions. But we definitely no longer get Peirce's law. That's the main point here. So at this point, it looks as if, well, maybe classical logic has lost, because it was it depended on a certain restriction on the format of our rules. And when we loosen those restrictions and go fully general, then we no longer have it. Well, I'm not sure whether the concept of fully general is well defined in this context, because, well, this was all presented now in natural deduction form, but we're all familiar with sequent calculus, and the same ideas here can be just recast in that format. So we have in the first line, we had just a few premises. That last one should be B. And from that, we infer something categorically C. And then we had on the second line, you will recall, I'll step back here one step. We had this saying that you have if you have A through B, and from each one of C through B to D, you can infer phi. Then you have phi. Well, that can be cast in the form of a sequent inference like this. And there are two rows here, but that's only in order for that the whole thing should fit into the table. These should be thought of as all on the same level. They're just sitting here on top of the inference stroke. So if we transform all the rules in our basis into this format, and then we add a couple of structural rules, and we say that these go into every basis, well, then we have, in effect, the same thing as we had before. We can write it this way, or we can write it like this. And if we do the same thing to the third form here, what I call the fully general one, well, then Peirce's law goes out the window. But now, once we have switched to this this different mode of presentation of our rules, then we see that, well, this can be generalized further. Just any collection of specific sequence can be taken as your premises, and as some specific sequence as your conclusion, and that's the rule. And then we can consider arbitrary collections of such rules, and we call that a basis. So this subsumes all of these three formats that we had on the previous rule. And if we go this far, well, as it turns out, we're back with classical logic by essentially the same proof that I flashed earlier. So there's no simple trend here to the effect that as long as we don't get too general, then we won't have classical logic. It's more a matter of switching back and forth. And I personally, I don't really know what to make of this. So I will leave you with two questions about this. To begin with, what is the theoretically most plausible format for an atomic base? Maybe I could mention here that whenever I speak with Peter Schroeder-Heister about this, he voices the opinion that, well, you should really go with just the simplest form, because as soon as you go more complex, then the items that you're carrying out your deduction on are no longer atomic in effect. You're in effect dealing with conditionals. He can correct me if this was a misrepresentation of his position. But, well, you might, on the other hand, say that, well, this is a pretty limited repertoire, if at least if you think of a basis as somehow representing the state of knowledge or the conceptual makeup of a thinker or a state of knowledge. So I think there are arguments in both directions there, and I don't really know what I think, how this question should be answered in the end. So second question, if we could settle that question, decide on an atomic base, on a plausible format for atomic bases, would that tell us anything about what the correct logic is? And this is how I started out on this. Basically the ambition was to save classical logic from Dummett. Now I don't really think of it in those terms anymore. Well, there you have it. And I don't have time to go through the proof. So thank you for your attention.
Thank you, Thor. Yeah, so it's my great pleasure to introduce you, Sara, and she's working at the University of Bochum, and she's going to talk about new ideas on proof-theoretic semantics. Go ahead, Sara.
Yes, thank you very much. Thank you very much for inviting me. Cannot emphasize enough how happy I am to be here among these speakers, and thanks to Elaine and David for putting this event up. So as you can see, I want to talk a bit about these distinctions of sense and denotation, and also identity versus synonymy of proofs. And let me start with just asking you about your intuitions concerning these two proofs, for example. Would you say those are the same? And if so, to what extent? So are they identical objects, or do they denote identical objects? Do they express the same meaning? So most of the time I discussed this with people. They said that yes, I mean, those are pretty much the same. They look very, very much the same. How about this example then? I mean, here you can see it's a bit more complex example. We have a proof in natural deduction and here one in sequent calculus. But it is, I mean, the same formula is proven. And as you can see, the rules of inference that are used here, the ones in sequent calculus correspond to the ones that are used in natural deduction. So in this case, people were often, a bit divided in their opinion. So basically half of the people would say, well, yes, you can say they are the same. And the other half was like, no, two different proof systems cannot be the same. Or maybe they refer to the same object, but in a very different way. What I want to argue here about is actually that this example and this example, that these are the same, in that they are both not only referring to identical proof objects, but that they are also synonymous. So they are also identical in meaning. So my main question here is, what is the meaning of proofs in a proof-theoretic semantics account? As we've heard today, proof-theoretic semantics started as an answer to the question, what is the meaning of the logical connectives? But then I think it makes sense to ask, okay, how do we get from this to the meaning of proofs as a whole? And I mean, since proofs are made up of applications of rules of inference, it makes sense maybe to say that the meaning of proofs must be in some way then based on the meaning of the connectives that are contained in them. And then there's has been an approach by Luca Tranchini, which this is based on here, where he makes such a distinction. I also want to make a distinction between sense and denotation for proofs. So he said he distinguishes for a derivation to have a denotation, this the proof object it refers to, and on the other hand to have sense. This would be it must contain only rules with reduction procedures available. I very much, I mean, I like this account and I agree with it. The thing is, okay, we can now say the denotation is represented by the derivation in normal form. Why in normal form? I mean, just because it's the most direct way of representation. I think, yes, that makes sense. But the thing is, on this account, we had no means to say what the sense is represented by. So you could only say whether or not a derivation has sense. So just yes or no, but not, I mean, if we then wonder about more detailed distinction, or if we wonder when does two derivations have the same meaning, then we would need something to specify the sense a bit more. So my question would be, what exactly does the sense of a derivation consist of? And so can we make a distinction between sense and denotation of proofs, which is a very, is a full-fledged analogy to Frigge's distinction that he makes for singular terms and sentences? And also what I was wondering about is, can we relate here different kinds of proof systems with respect to such a distinction? So I'm only concerned with natural deduction and sequence calculus here, but so the question would be, do two derivations with the same denotation in different proof systems, do they always then differ in sense, or can sense be shared over two proof systems? And if we go back to my example in the beginning, then you can see, yeah, in my opinion, sense can be shared. We can have two derivations into different proof systems which have the same sense. I will tell you why in a bit. So the basic approach here is to exploit the well-known Curry-Howard correspondence and use proof systems that are encoded with lambda terms. Why I think that makes sense? In the literature, it has been pointed out that it makes sense to use these systems if, for example, we want to make the structure of derivations transparent. So if we're not only interested in mere provability, so is the formula provable or not, but in the structure of how it can be proven. And also it has been pointed out that it allows an easier comparison between different proof systems. And I mean, I'm interested in both points here, so I think it makes sense to go with these term annotated proof systems. And what you can see here, for example, I mean, there can be, of course, there's different ways to go from the same premises to the same conclusion. Not only in different kinds of proof systems is this possible, but also within one proof system. And for example, here, I think this example was by Troeltz and Schwichtenberg. This would be an example where without the term annotation, these proofs would look exactly identical. But with the terms, it is one way, at least, to make these distinctions visible, so transparent. I mean, this also, of course, this is because the principal types of these terms are different. So the principal type of this could be a derivation also of B implies A implies B, whereas this would be then, for example, B implies A. And this is one way to make this transparent. Okay, and what can we say now about distinguishing sense and denotation in proofs? So what has been, so this is not just my idea here, but this has been proposed at various points in the literature to say that the denotation of a derivation is referred to by its normal form, or here, because I'm using terms, the normal form of the term that denotes the sequent or formula to be proven, which I would call the end term. So the end term is the term that decorates the conclusion. So, and then we can say two derivations with beta eta equivalent end terms denote the same proof. there is a discussion whether this eta equivalency is correct to take in, but I will not go into detail about this here. The thing is, okay, about denotation, there has been some something in the literature, and also about sense, but not that much. And especially the focus concerning sense has so far been often to or just between normal and non-normal terms, for example. Or if we go for proof systems now, it has been pointed out that if we have a proof in non-normal form and one and the corresponding proof in normal form, so it reduces to this form, then we could say, okay, they have the same denotation, but they differ in sense. Or correspondingly, for proofs in sequent calculus, then proofs containing an application of cut versus a cut-free proof. But as I pointed out in the beginning, I'm also interested in comparison between these proof systems. So what I want to suggest here is to say, next to this definition of denotation of a derivation, to say that the sense of a derivation consists of the set of terms that occur within the derivation. So the n term, the denotation, but the terms, all the terms that occur within the derivation make up the sense. Let me tell you a bit why I want to propose that, a philosophical motivation for this. If we look in the literature, what is conceived of as Phrygian sense, for example, Damit says it's a procedure to determine its denotation, or Girard says in a piece about in the context of proofs as programs and so on, he says, okay, sense can be a sequence of instructions, and if we then think that terms represent programs, then the purpose of a program is to calculate its denotation, then I think it would make sense to say that these terms occurring within the derivation make up the sense, because we can have the case that the proof is essentially the same, but the way it is given to us, the way the inference is led, that differs. And this actually can be then read of the set of terms occurring in this derivation. So they end up building the same term, but the way this term is built up differs. Then we can say, so the procedures to determine the denotation differs, which would be the sense, these procedures. And this would then allow us to compare differences in sense within one proof systems, but also over different proof systems. And now further, before I give some examples about this, for some cases that Frege considers, because as I said in the beginning, I want to see how far we can take this analogy between Frege, sense and denotation, and what I consider to be sense and denotation of proofs. So with Frege, we have one case would be that we have different signs, but still this doesn't result in a difference in sense. So we have the same sense, and then of course always the same denotation, because the sense must determine the denotation for Frege. And examples for singular terms would be Gottloob's brother versus the brother of Gottlob. Or for sentences, he gives an example: M gave document A to N versus document A was given to N by M. So just these are then minor grammatical differences. Or also another example that he gives is we can have different words in different languages, of course. So we can have snow in English and Schnee in German and neige in French. Of course, these are different words, different signs, but he would say they have the same sense. They don't differ in sense. Another case would be that we have different signs, and this goes hand in hand with a difference in sense, although we have the same denotation. So famous example, I don't need to go into that, is morning star versus evening star. Both refer to the same object, the planet Venus, but in a essentially different way. So to give you examples now to what I think this corresponds to in proof theory. Would be my examples from the beginning. So here I would say, yes, I mean, we have different signs because we just use different variables. We use different atomic formulas, but this doesn't result in a difference in sense, I would say. I mean, the proofs are, if we are talking about the meaning of proofs, then the structure of the proof is decisive, but not like whether we prove P implies P or Q implies Q. So here I would say these are synonymous, and also we can think of this of the characterization by Göran Sundholm about this for sentences, where he said that we must have the same epistemic attitude. So it cannot be the case that a person has different epistemic attitudes towards the same sense of sentences. And here I would say, if we say, I mean, if you're competent in proof theory a bit, then you cannot say this is valid, but this is not, for example. So I would say this is the same here. Another case would be where we have where the way of inference is essentially different because different operations are used. So here, I mean, we can see if we compare this and this, something different happens here. Yes, but the denotation would be the same because the n terms share the same normal form, because this term can be beta reduced to this. So this would be one of these cases where we say, okay, here we have a non-normal proof, a normal proof, but so denotation the same, they are identical, but not synonymous. Or an example in sequence calculus where this, because non-normal derivations, of course, correspond to derivations with cut in sequence calculus. So here we would have the case that the same n term comes out. So the denotation would be the same, but they are not synonymous because we have this, I highlighted this in red because this does not occur here. The other terms are the same, but this only occurs in this derivation. So yeah, the operations are different here. So they are not synonymous, say. Now to this, one of these more complex examples from the beginning that are maybe more controversial than the one I gave before. Here we have a derivation in natural deduction and one in sequence calculus. And I would say they are identical and synonymous. Identical because, I mean, the n term that is produced is the same. And I mean, here we have of course, there's a difference in signs. This is not disputable. We have different proof systems, different ways of writing the proof down. Yes, but exactly the same operations are used here. So the set of terms that occur within the derivation are exactly the same. So I would say the meaning is given, yeah, is expressed in the same way. So they are synonymous. Yeah. And also, yeah, if we think of, that's why I mentioned it before, Frege's thing with different languages, I always think of this a bit here, to think of different proof systems kind of as different languages. I mean, different ways of expressing the same, basically. So yeah, if you would accept this, then I would say this fits also to the analogy that we just have different languages, but they can yeah, express the same sense. Just quickly, some to just say that this analogy would also hold for the cases that, according to Frege, should not happen. What is not supposed to happen, according to Frege, is that we have one sign but different senses. So that be ambiguous terms. Of course, happens in natural languages. So in English, we would have bank, for example. We can have Bank of the River or the Money Institute. But he says in formal languages, it should not happen. And of course, here we are in a formal language, so it shouldn't happen here, and it cannot happen. luckily, because I mean, it cannot be that we have exactly the same signs. Would mean we have exactly the same terms, but different senses would not work here. And also another case that should not happen is that we have one sense but different denotations. The sense should always determine the reference according to Frege, and this cannot happen in our framework either, because the end term is always part of the sense denoting set. So it cannot be that we have exactly in one sense, but somehow different denotations. Okay, so to conclude, I think this Fregean distinction between sense and denotation can be used in our proof context to make a more fine-grained distinction than we had before with respect to proof identity and synonymy. And we can say that the denotation of a derivation in a system with lambda term assignment is referred to by the end term of the derivation, and that identity of a different calculi or within the same calculus consists in having end terms reducible to the same normal form. And on the other hand, that sense of a derivation in a system, in such a system, consists of the set of terms that occur within the derivation. And the senses are different when the way of inference is different. If not, then we can say that they have the same sense, that they are synonymous. And just a quick outlook, because it was mentioned by Peter Schroeder-Heister in the beginning. Of course, this has to do with reduction procedures here. As I said in the beginning, Luca Tranchini's approach was to say a necessary condition for a derivation to have sense at all. It must be made up of applications of inference rules that have reduction procedures available. So some nonsensical connectors like tonk do not have acceptable reduction procedures. So we can say those are meaningless, but we need a criterion then for acceptability of reductions. What reductions are acceptable and which are not? I mean, this was a question that I recently tried to answer in another paper, but it's not concerned here. So thank you very much for your attention. And
thank you, Sara, for the very nice talk. It was fantastic. Okay, so now we go to the last talk of the session now. Yes, it is Luiz, right? Luiz, you're going to share your slides? Yeah. So it's a great pleasure to introduce you, Luiz Carlos Pereira, and he's a professor in Brazil. And welcome, Luiz, and thank you for accepting the invitation. So go ahead. Luiz, we cannot hear you, so.
Can you hear me now? Can you hear me now?
Yeah, now yes.
Okay. As the other speakers, I would like to thank Eleni and David for the kind invitation to take part on this in this meeting, and for the great opportunity to meet some old colleagues and some old friends again in this meeting. So my intention today is to present very briefly some connections, at least some superficial connections between two projects, the project of proof-theoretical semantics and the ecumenical project, specifically with respect to classical logic. Let me start with some very, very basic facts about the ecumenical perspective. What is an ecumenical system? In a very general sense, an ecumenical system is a codification where two or more logics can coexist in peace. And what does it mean to exist in peace? The idea is that different, and maybe, and this is the interesting case, maybe rival logics can accept and reject the same things inside the codification. They accept the same principles, the same rules, the same consequence relation. Ecumenical results, or the ecumenical perspective, has been published in several different works. Peter Krause's, I think this was the first ecumenical codification. It was not published as a paper, it exists just as a technical report from 1992. And then we have Prawitz from 2015, Gilles Doek in 2015, quite recent work from 2021, and a lot of work by Sonia Maran, Eleni, myself, Emerson, Valeria, 2017, 1921, and the group of the WEC, maybe should include here the name of Dale Miller also as working this, at least related work with the ecumenical perspective. As I said, the first ecumenical system was proposed by Peter Krause in 1992, although he didn't use the terminology ecumenical. Now, Krause proposed a sequence-style natural deduction codification with classical and constructive operators. In 2015, Prawitz proposed another ecumenical natural deduction, Gensen-style natural deduction, where classical logic and intuitionistic logic could coexist in peace. In the same year, Gilles Dweck exploited ecumenical ideas by means of an embedding of classical logic into intuitionistic logic. Several developments of the ecumenical perspective in modal logic and pure systems follow the steps of these seminal works. But it's interesting to observe that these ecumenical codifications, they were defined with different aims. And now I describe very briefly these different aims. Krause's main objective was to propose a logical framework where, first, all proofs are constructively valid, and classical proofs may be incorporated inside this codification, preserving their familiar structure. This aim or this objective clearly includes Krause's proposal in the area of extraction of constructive or algorithmic content from classical proofs, right? This is a nice quotation from Krause's paper. The indiscriminate use of elimination of double negation extinguishes all finer distinctions in classical proofs. This makes it impossible to trace constructively parts of classical reasoning. And this is very important for my talk today. This idea of looking at a proof and being able to trace some parts which are not classical, which are constructive inside a classical proof. And Krause continues, however, as soon as the classical mathematician is interested in an algorithmic interpretation of his results, he ought to locate places where he uses elimination of double negation. Again, this is very important for our project, the ecumenical project, this idea that look at the proof. The proof may have constructive parts. How to locate these constructive parts where we need to use classical reasoning. The main motivation of the work was similar to Krause's, to explore the possibility of hybrid readings of axioms of mathematical theories in proofs. The example discussed by Krause is the axiom of choice and an application to algebraic number theory, and the example discussed by Dweck is also taken from set theory. Prawitz's main motivation was to extend an inferentialist semantics, Gensen-type inferentialist semantics, to classical logic. The real arena of the disagreement between a classical mathematician or logician and an intuitionistic mathematician or logician is the arena of meaning theory. In this arena, according to Dummett, two theses should be established. A positive thesis that establishes a coherent meaning theory for intuitionistic logic and mathematics, and also a negative thesis that established that the classical ideas, is a quotation, that the classical ideas about meaning are mistaken and that no intelligible meaning can be attached to the logical constants agreed with the classical use of them. Dummett is not easily caught in Quine's trap. Quine's trap is no real disagreement, just different languages. For Dummett, there is a distinction between, quotation, conceptually trivial and conceptually deep disagreements. A trivial disagreement can possibly be solved by the introduction of two different words with different meanings, while conceptually deep disagreements concerns the very notion, the very conception of what meaning is. Prawitz seems to agree with Quine when he says, when classical and intuitionistic codifications attach different meanings to a constant, we need to use different symbols. And for dog, I shall use the subscript C for the classical meaning and I for the intuitionistic. The classical and the intuitionistic constants can then have a peaceful coexistence in the language that contains both. What's Prawitz's main idea? Well, we have different symbols, a symbol for a classical and a symbol for intuitionistic, but, and this is the important thing, the same meaning explanation, right? Classical logic and intuitionistic logic coexist in peace. In Prawitz's systems, we would have a constant for conjunction, or constant for the absurd, and constant for negation, and the universal quantifier, but an intuitionistic implication, a classical implication, an intuitionistic disjunction, a classical disjunction, an intuitionistic existential quantifier, and a classical existential quantifier. Well, let's move now to proof-theoretical semantics. In the first paragraph of Piecha's contribution to SAP, to the Stanford Encyclopedia, we read, proof-theoretical semantics is an alternative to truth-conditioned semantics. It's based on the fundamental assumption that the central notion in terms of which meanings are assigned to a certain special language, in particular to logical concepts, is that of proof rather than truth. In this sense, proof-theoretical semantics is semantics in terms of proofs. Proof-theoretical semantics also means the semantic of proofs. Peter mentioned this distinction today, and Dag also mentioned this distinction today. And I think that the ecumenical perspective has something to say with respect to both these senses, the sense of semantics in terms of proofs and the semantics of proofs. Now, with respect to the semantic of proofs, I would start with a common criticism that ecumenism has suffered, is that ecumenism is, it adds nothing new to double negation translations of classical logic into intuitionistic logic, or even minimal logic. The classical operators could simply be introduced by explicit definitions via translations, for example. The translation of the classical disjunction is the expression, and in the expression A or classically B, for example, would just be an abbreviation for not I, and not B. In this way, the new classical operators could be considered just as a convenient notation device and could be eliminated. But although very closely related to double negation translations, the ecumenical perspective is not the Gens and Gödel negative translation. And Krauss makes this point very strongly in his technical report on page 20. From a constructive point of view, there is no reason to translate the occurrences of implication and disjunction and interpret A implies A or B as not the translation of A and not the translation of A and not the translation of B, where G is the Gödel-Gensen translation. Krauss correctly points out that we cannot find a uniform method for describing the places in familiar classical assertion where intuitionistic logical operators are being used, where classical operators are being used, because this depends on how the assertion under consideration is actually proved. So it depends on the proof. I cannot just look at the assertion and say, oh, these occurrences will be classical, these occurrences will be intuitionistic, these occurrences will be classical, etc. But given the proof, I can, as I said, when I use the first quotation by Krauss, I can locate exactly the places where we should be classical and the places where we can continue being constructive. And the moral here is, the proof is responsible for where we have to be classical. If we still think in terms of translation, we should think about translating proofs and not just assertions. The ecumenical perspective permits that given a proof, we locate exactly where we need to be classical. And here we have some interesting examples. For example, in this proof of A implies B or A, we can see that I need to be classical with respect to disjunction here, but not with respect to implication. We have been discussing Piecha's law in Sandqvist's presentation, and here we have different readings of Piecha's law, where all implications are classical, where the first implication is intuitionistic and the two other implications are classical, where the only classical implication is the last one. And the proof of these last sentences is here. I will skip the proof here. And this is also another interesting example is given by Krauss, where some interesting relations between ecumenical quantifiers and ecumenical implications are shown. For example, these three expressions are all equivalent in an ecumenical systems. And you see here that you have a universal quantifier and a constructive implication, an existential quantifier, intuitionistic extension, and you can change, I mean, they are all equivalent. I can change this classical quantifier by intuitionistic quantifier, changing the implication from intuitionistic implication to a classical implication. So it depends, really, it depends on the proofs where we should locate the place where we are being classical and where we are being intuitionistic. I have here the proofs of all these equivalents, but I will skip the proofs. But I would strongly suggest that to do proofs in the ecumenical systems, to see clearly this idea of tracing constructive paths and locating where we should be classical. The motto is here, ecumenism refines our way of looking at classical proofs, right? So let's move now to the semantics in terms of proofs, right? Julien Murcy as Dummett seems to adhere to the negative thesis that the usual classical codifications do not satisfy some basic requirements of inferentialism or proof-theoretical semantics. And I quote Murcy, according to logical inferentialists, the meaning of logical expressions are fully determined by the rules for their correct use. To keep proof-theoretical requirements on admissible logical rules, harmony and separability directly stem from this thesis. However, the standard single conclusion assertion-based formalization of classical logic probably failed to satisfy. But again, according to Murcy, even Prawitz rules for classical operators should not be accepted by a strict inferentialist because they do not satisfy the separability requirement, since the formulation of the classical rules use negation. They are not, as we say, pure. And here you see the rules, Prawitz rules for classical disjunction and classical implication. And you see here that the introduction rule for classical disjunction uses negation in the assumptions that are discharged. And the classical rule for classical implication, we have also negation here in the consequent, in the assumption that it is discharged, right? Several different proposals have been present, to deal with this, this question of purity or separability. One of them, very interesting, is Murcy's proposal that combines in a very interesting way Peter's idea of higher level rules with Tennant's idea that the absolute should be conceived not as a proposition, right, but as a punctuation mark, right? And I have here some nice quotations about this notion of punctuation marks. This is the original Tennant quotation. An occurrence of bottom is appropriate only within a proof as a kind of a structural punctuation marks. It tells us where a story being spun out gets tied up in a particular kind of knot, the knot of a patent absolutity or self-contradiction. This is a nice quotation by Wittgenstein from Zettel. Contradiction is to be regarded not as a catastrophe, but as a wall, indicating that we can't go here. And here's a nice quotation by Brouwer. The words of, it's from it's in the first page of the third chapter of Brouwer's thesis. The words of your mathematical demonstration merely accompany a mathematical construction that is a fact without words. At the point where you announce the contradiction, I simply perceive that the construction no longer goes, that the required structure cannot be embedded in the given basic structure. And when I make this observation, I do not think of a principium contradictionis. And this is again a very general remark by Wittgenstein from the Tractatus. Signs for logical operations are punctuation marks. Right? This is what the impure rule that we saw here. Prawitz, according to Murcy, are impure or do not satisfy a purity requirement. This is what this impure rule becomes in Murcy proposal, right? Here we have where Peter's ideas comes in. We are assuming a rule that takes us from the premise A to the bottom, a rule that takes from the assumption B or to the premise B to the bottom. And then when we apply the classical disjunction introduction, we discharge these rules. So we have this Peter's idea that we have not just assumption formulas, but assumption rules and rules that can discharge rules, right? And this is the pure rule for classical implication introduction, where again, instead of having not B, we have a rule that leads us from B to an end point, right? And here again, this is an example of Peirce's law being proved in Murcy's system, right, where we use this this combination of ideas of Peter's abstract or generalized rules or higher level rules and the conception of the bottom as a punctuation mark. A different approach, right, that we have been pursuing now, myself, Elaine, and some other people, is based on Girard's old proposal of systems with the stub. A sequent, if we look at sequent calculus, a sequent with the stub is an expression of this form, where we can distinguish different regions in the succedent of the sequent, right? We have the delta here would be a classical region, and the pi would be the stub where the inferences go, really, where we apply the inferences. And these are examples of rules in sequent calculus with the stub. This would be the classical rule for implication with the stub, and the classical rule for disjunction with the stub. And here I have a natural deduction rule using the stub, right, for introducing the classical implication, right? There are a lot of things to be done in this area. And here's again the proof of the Piecha's law using a system with the stub, a natural deduction system with stub, which in a certain sense is pure, right? And I conclude with some future and ongoing work, really. A lot of things, many, many things to be done. Comparison, given that we are talking about translating proofs, a comparison with Jens Brage ideas of a natural interpretation of classical proofs, comparison with Restel's proposal for a classical natural deduction system with the rule of alternative, further investigation of the form of normal deduction ecumenical systems, application to real mathematical theories. We saw here today the importance of atomic basis, and to discuss proof theoretical semantics at the atomic level. Yes, we do have to do a lot of things about ecumenism at the atomic level, comparison with combination of the general area of combination of logic, algebraic ecumenism, further investigations between normalization strategies and ecumenism, further investigations of the relation between ecumenism and the structural approach to logicality, as we saw in the presentation by Thomas. So many, many things to be done in this area. So thank you very much for your attention.
Thank you very much, Luiz. Very nice talk. So it's my great pleasure to invite Edmund Robson to talk on this World Logic Day meeting of UCL. And Edmund is going to talk about a work that he's been developing with David and Eike. And so Edmund, it's all yours now.
Thank you so much. And thank you so much to everyone, to you for inviting me, and everyone for the really interesting talks that they've been giving. This is definitely moving into the ecumenical section of the meeting, because I think that we're coming at this area from a rather different perspective, and I hope very much that some of the things I say might be interesting to you, and that you have responses to the kind of prods that I'm going to try and the pushes that I'm going to try and make to you. So broadly speaking, the area that the way that we're coming in is from logic as a modeling tool rather than a purely foundational investigation. So there are lots of areas where we want to use logical tools, and conventional semantic accounts, conventional accounts for proof theory basically don't apply. So we're really interested in understanding kind of more about the philosophical justifications of proof theory, so that we can apply it in lots of different proof systems that we're actually interested in using. And in that connection, we've been looking at a couple of really nice papers by Thomas and Piecha, Thomas Piecha and Peter Schroeder-Heister. First on incompleteness of intuitionistic propositional logic, and secondly Tor's work, for which the key reference for us is this nice paper on base extension semantics that he's kind of talked about in his talk. So for those few of you probably who are not familiar with intuitionistic propositional logic, let me just remind you It's given, I'm giving it here in the natural deduction form. It's given by rules in which, let me see if, I'm hoping you can see, you've got premises on the top of rules and conclusions on the bottom, and the rules split into the blue ones, which are introduction rules, and the red ones, which are elimination rules. And it's part of the background to this area that the introduction rules are driving the meaning of the connectives. And in some sense, the elimination rules are expressing the completeness of the introduction rules. And I'm guessing that idea is familiar with both. So I've put here the rules not in quite standard format, but I've put them in ways that kind of slightly more systematically express that completeness. So for example, we've got no eliminations for no introductions for the bottom connective, and the rule for bottom expresses the completeness of that fact. Okay, so starting with Peter's paper. Peter's paper is, sorry, Thomas and Peter's paper is centered on characterizing times when a semantics is, when intuitionistic predicate calculus is going to be incomplete for a semantics. And the particular thing that they're using most in that is Harrop's rule. So Harrop's rule I've written here, it says that if you can prove not A implies B or C, then you can prove not A implies B or not A implies C. And that's admissible in intuitionist predicate calculus, but it's not critically not derivable. And let me just say it's let me see if I can do this. It's an enhanced form of the disjunction property. And so basically, so it's admissible, but it's not derivable. And therefore, if a semantics admits the rule, then intuitionistic propositional calculus is not complete for it. Let me just scribble on this and replace that not A implies by a theorem sign, that not A implies by another theorem sign, that not A implies a theorem sign, and that disjunction by an external, or I'm sorry for the large fonts there, and you'll see that this is really closely linked to the disjunction property. If you can prove B or C, then you can prove B or you can prove C. And that makes it not a kind of ad hoc example, it makes it an important example because the disjunction property is really important for people who are interested in constructive reasoning. And what Harrop's rule in essence is doing is it's to some sense it's internalizing the disjunction property by hiding it behind a not A implies B. Sorry, not A implies, in order to internalize it. Okay, so sorry, I'm going to have to delete, annotate and delete all that. Okay, so I can skip that slide on the disjunction property, and I think I can skip this on the generalized disjunction property. So in order to talk about this, Thomas and Peter introduced a kind of framework for their semantics. So not talking about these being particular, it's not saying that every example is a proof-theoretic semantics, or that every semantics fits, but their particular assumptions are that they have a non-empty finite or infinite set of entities called bases, and that each base has an associated consequence relation. And then, so that's the basic structure. And then they have, there are some key properties that they require. And the first two are that if something is valid at a base, if it's the consequence of no assumptions. So if we've got a conjunction valid in S, then A and B is valid in S, then A is valid at S, and B is valid at S. And similarly for disjunction, if A or B is valid at S, then either A is valid at S or B is valid at S. So that's a baking in of a form of disjunction property there for each base. The only point at which the consequence relation is used in full rather than the validity is for implication. So here we've got that an implication A implies B is valid at S if and only if B is a consequence of A. And that's the only point at which the consequence relation is really used. Then there are a couple of more conditions, one of which is the definition of a global models relation, and the other of which is an extra condition on it. I'm not going to take that as particularly important. So I was brought up to look at examples and, equally importantly, things which are not examples. So here I've got two families, one of which is strictly logical examples 1 and 2 derived from provability. And on the other hand, we've got, in the other column, we've got a column of examples derived from Crippy and sheaf models. And if you look at that, you'll see that the bottom row are things which are not examples and the rest are, but they're not examples because of the failure of the disjunction. So being more specific, if we want to look at, I'm going to go clockwise around that diagram, starting in the bottom left-hand corner, but with a non-example, provability with respect to arbitrary theories. So for that, the bases would be simply a collection where each base contains a set of propositions and the consequence relation is provability with respect to those propositions. So standard consequence when you add the propositions into your assumptions. So here we've got that provability. That's not a consequence. That's not an example very obviously, because if we take delta to be A or B, then we have delta proves A or B, but delta does not prove A and delta does not prove B. So this is a clear non-example, and it's an example we actually want to use because, for example, we have disjunctions like that in the theory of Heiting arithmetic, in the theory of reals, and theory of fields, and theory of local rings, endlessly. On the other hand, if we look at provability with respect to disjunction-free theories, so now the crucial fact is that our delta is a set of disjunction-free propositions, then the disjunction property now holds by the generalized disjunction property for intuitionistic predicate calculus. So if we have delta proves A or B, where delta is disjunction free, then it is the case that either delta proves A or delta proves B. And an important example of that is where each delta is a set of atomic formulas generated by atomic systems. So So we've got the kind of base system examples that we've also been talking about included in this provability example. The third example, and this is already in Peter's paper and Tor's mentioned it, is Crippy Models. So our set of bases is a set of worlds. Our satisfaction relation, the satisfaction relation we're going to use is standard Crippy forcing. A is satisfied at world W if W forces A, and the consequence relation is the internal consequence relation. So the extensional one, the one that says gamma gamma implies A, if and only if at W, if and only if for all worlds W primed containing W bigger than W, if W prime forces everything in gamma, then W prime forces A. And this is the standard interpretation of propositional logic in the Crippy structure. So it's sound and it follows it. More or less identical to that, I'm a category theorist, so I have to give you pre-sheaf models. I think the key thing you need to know about pre-sheaf models, they're two things. Well, they're based on a topos of functors from C up to set, where C is a category. Being category theorists, we're naturally annoying, and we've reversed the direction of the arrows. So the bases, again, are just a set of objects. The Crippy forcing is almost exactly the same. And again, it's a standard interpretation of propositional logic in this structure. Okay, so we've got Peter's model, and there are lots of conditions under which he's produced lots of conditions under which it's not going to be complete. I'm now going to turn to Tor's model, and Tor's construction for us splits into two parts, one of which is a novel definition of forcing, and the second of which is its use in the construction of a specific complete model. I'm mainly going to talk about Tor's forcing. So the particular claims I'm going to make are that his forcing construction can be used on any Crippy frame, given an interpretation of a set of atomic formulas. Secondly, that it's an example of sheaf-theoretic forcing. And thirdly, that the topology used for the forcing is related to continuation semantics in programming, and a number of other things. So for Sandqvist forcing, if you simply read his definition, it doesn't use the structure of the base, it just uses which structure of which atomic formulas are satisfied in each base. So the definition for atoms is that B forces P is forced at base B, if and only if P is provable in B. I could simply give that as data. I could simply tell you the bases at which P is valid. It doesn't reflect the fact that the base is constructed using atomic rules. The conjunction and implication for clauses, once you unpack them, are exactly as for Crippy. So I won't go into those. But the non-standard part is that B forces A or B, if and only for every atomic formula P in his set, and for every C containing B, if C forces P and C forces A implies P, and C forces B implies P, then C forces P. That's again unpacking his definition. But again, that's equivalent to for all P, B forces A implies P and B implies P implies P. Or using a slightly different intuitionistic equivalence. So that is the equivalence that Tor has been focusing on. And the equivalence that I want to focus on slightly bit more is this second one that A implies P and B implies P implies P is equivalent to A or B implies P implies P in standard intuitionistic logic. And similarly, we've got the same clause for bottom, B forces bottom, if and only if B forces P for every atomic P. And that's equivalent to, for all P, B forces bottom implies P implies P. And that's because bottom implies P is true and bottom and true implies P is P. So both of these are fitting this implies in P implies P structure. And that's a topology. So a bit of background, I'm running out of time. Sheaves are very important mathematical structures. And for us, they're important structures because we have sheaves of groups, sheaves of rings, sheaves of modules. Those behave like groups, they behave like rings, they behave like modules. But if you take the classical definition, a group is a set with certain operations. A sheaf of groups is not a group. Nevertheless, we want to talk about them in the same context, use the same kinds of theories by them. But technically, sheaf of groups, not a group. So in Tor's model, so we've got this this kind of Crippy model with a topology, and the difference between a sheaf model and a standard Crippy model is precisely that you've got this closure operator, a J operator. And what the J operator does is truth values in Crippy models are upwards closed sets of worlds. So we have a collection of sets of worlds, The order relation represents increasing knowledge, which means restricting the set of possible models. So as you go up in the Crippy model, you get smaller in the sense of the number of possibilities that it, more refined in the sense of the number of possibilities that it represents. This means that you can have two different upwards closed sets, which might cover the same collection of end possibilities. And in Crippy semantics, you can have a proposition which is true on one of those sets and not true on the other. Sheaf semantics allows you to specify that things which cover the same end possibilities have the same interpretation of propositions on them. So that effectively what you're doing is you're taking a union of all the end possibilities. So J of U is intuitively, if we've got a set of possible worlds, our closure operator is intuitively going to give us a set of possible worlds which are greater than or equal to the union of all the worlds in the set. So they're refinements of the union. There's a bunch of abstract characteristics for that. One of the examples is implies B for any B. Tor has used implies P for a collection of atomic propositions, and then for all quantified over them. So it's for all is taken over the chosen set of atomic propositions. And this is sheaf theoretic semantics. Okay, so it can be used in a general Crippy frame, corresponds to a sheaf model. Because it's got this relation to union, it does not satisfy the disjunction property, and so is not an example of the Piecha Schroeder-Heister semantic framework. But this topology, if P is bottom, A implies P is the double negation topology. And in general, this kind of topology is linked to variants of double negation translation and continuations. And what crucially continuations are doing is, for people in programming, is it's formalizing a symmetry between production and use. So in computational terms, a continuation is a rest of the computation that you do after you've produced your value. So it's not the computation you do to produce the value, it's the rest of the computation you do afterwards. So in this AR as P, P represents possible outcomes of the computation. And the continuation semantics typically will take an expression and a continuation and produce an outcome. And it's used to model non-standard flows of control. So picking up on kind of things from the last talk, it's if your attempted proof has produced an error, transfer control to an error handling routine in a structured and principled and constructed way. So they're very much used in this kind of framework. And I am, I think, well over time, and I should probably stop there. So I did have a couple more. Well, I had too many slides, but one pointing out that the issue here is with disjunction, and for a category theorist, and implies are both right adjoints. Disjunction is a left adjoint, and it implies the introduction rules are invertible in standard calculus. For disjunction, in some sense, it's the elimination rule that's invertible. So there are interesting things going on there. But I should definitely stop, and thank you for this opportunity.
Thank you, Edmund. Thank you so much.